Testing. Hello. Hi. 1, 2, 3. Surprise Sunday stream. Because I would normally not be able to do this, but this is a surprise, I suppose. I hope it's a good one. I really don't like surprises. Anyway, hello. Happy Sunday or happy late Saturday. Whatever the case, inshallah it's happy. Well, yeah. Let's go. I don't think I have any updates yet. For today's stream, I want to be able to go through this. Happy start of the day. Thank you. Inshallah, it will be happy. Yes, okay. We watched the video that didn't really say anything, and then we're in the gathering data part. Happy weekend, I suppose. Okay. The stream might be like an hour and like 15 minutes, so that's about the time I have. Yeah. Okay. So today's lesson is about training a language model from scratch. Probably, I'm guessing it's going to be a generative language model. So yeah. Starting off with the gathering data part. Okay, let's snooze this. What? Why do I have one snooze left? Okay. Python code, not cod. This is not a fish. Is abundantly available from repos such as GitHub, which, by the way, the weather is like, I would call this weather cold. Like, it's actually cold outside. Can I check the temperature? It is 9 right now. Huh, that's pretty cold. Yeah. Okay. I like it. So we can use to create a dataset by scraping for every Python repository. Scraping for data in a place that has the thing that we want. Okay. This was the approach taken in this book to pre-train GPT-2 that used a GitHub dump of about 180 gigabytes containing roughly 20 million Python files called Code Parrot. That sounds cool, yeah. I don't have a warm beverage actually. I have ayran, but like the simplest form, water and yogurt, nothing else. It's really good. Yeah. It's a lukewarm beverage. I prefer things to be lukewarm. Authors build a dataset that they shared here. However, training on a full corpus is time and compute consuming, and we only need this subset of the dataset concerned with the Python data science stack. Okay, so we are filtering by Python code because and only the data science part. So that's actually nice. Okay, let's start by filtering the code parrot dataset for all files that include any of the libraries in the stack. Okay. Because of this, of the dataset size, we want to avoid downloading it. So we're streaming it. Instead, we'll use the streaming feature to filter it on the fly. to help us filter the code samples using the libraries we mentioned earlier. We are using this function that lives in tropic areas. Used to tease me in the winter. Too cold last night. It got down to a low of 15. Wow. Like somewhere around the equator. No, it gets down to like 0 or minus here. Like definitely, but not that much minus. Like I don't think we go past what, -3, -5. So it's not like the north of north, or maybe probably south of south. But yeah, I like the fact that we have all the seasons. Mm. But yeah, it's fun to gaslight the other side of the planet to say winter is coming, and they're like, no, summer is coming. Like, oh my god, no. um, so yeah, I'm sure you're used to being gaslit. Cause like, um, I don't. I guess I don't watch enough entertainment from the uh southern half of the earth, but every entertainment that I've seen, it's like December cold, July hot, you know? Um, so yeah, must be annoying as a child to see nothing matching your. I mean, I have had the problem of things not matching my style, but that's different. Should probably go copy the code because I need to do the login and the. Should I go and copy the code? I'm gonna do that. Going to collab. Yeah, summarization. You open and then you open. Open. Yes. People from the US and UK get weird hearing about a hot summer Christmas. Yeah. They are very connected to their white Christmases. Okay, let's copy this part. Put it here. We barely get snow. I mean, no, I mean, it's just like where I live, there isn't much snow, but you drive 30 minutes and then you get to snow. So it's not that bad. But yeah, we don't get much snow. And when we do get it, it becomes like an event because like we got it like a few years back, stuff like that. Okay. So if we see anything like this, we take the whole file, right? That's the idea. They're true and false. If keyword in keyword, and the string. Okay. We can use this to create a function that will stream the data set and filter the elements we want. All right. So the idea is filter streaming data set. We get the data set and then we have a dictionary list. You're kidding. You're not kidding, right? You're kidding? Snow, yes, the thing that falls from the sky. Really? But it doesn't it snow? Huh. I don't know. Guess I don't have enough information. So we say iterate over the data set, and then if Oh, is that the any keyword? Oh, okay. So if true, any keyword. Okay. Ah, but doesn't that, what are we taking? Sample items, filtered dictionary, we append, for this item, we append this. We're not taking one line of code. We're supposed to be taking the whole file, right? Let's get to here. Run before. Oh, what am I connected to? Whoops. I think I'm gonna need to disconnect. Disengage. What am I connected to? Stop. Yes. CPU. Got it. Sure. I know if I use GPU a lot, I normally get like locked out. So let's see how much we can use. Okay. So, we are running this on the training split and we're filtering by pandas, sklearn, matplotlib, and seaborn. Okay. Huh. Wow. So here it says 3% of the data set is returned after this stream. Huh? Sure. Okay. Now let's see how much. Is it the same 3%? Probably gone higher. So we're taking a bit time consuming. Okay, so here it's 326. I'm guessing it's higher because GitHub doesn't stop growing. This leaves us with about 3% of the original data set, which is quite sizable. Is it still? 3% of 180. Around like 6 gigabytes. And it's like 600,000 Python scripts. Wow. Filtering the dataset can take what? 2 to 3 hours depending on machine and bandwidth? Dude, you should have told me earlier. I mean, I wouldn't have run it. But apparently that takes 2 to 3-ish hours. Okay. If you don't want to go through this lengthy process, we just take the filtered one. That would be lovely. Is that the code that's coming up? Yeah, I'm gonna pause you. I'm really sorry. Thank you for your service. Okay. And we take this. We have training and validation. And what does the S stand for? It's just filtered, right? Okay. And it consists of, 600,000 rows. And each of them has like a file of code probably. Cool. What is the size of the file? Or is it like a folder because it's a repository? Retraining the language model will take a while. Right? I mean, obviously, yeah. We suggest that you first run the training loop on a sample of the data. By uncommenting where? Uh-oh. I'm gonna pause this again. I should start reading before I just run code. So if we uncomment this, we get a subset. Which is good. There. Okay, so we did that. We uncommented the line above. Make sure that the training successfully completes and the models are stored. Nothing is more frustrating than training run failing at the last step because you forgot to create a folder or because there's a typo at the end of the training loop. I agree with you. Okay, so here's an example from the dataset. Let's get an example. I mean, it is loading, but this time, oh, 8? Why 8? Wasn't it supposed to be 6? But it's like, it's a subset of a subset. MashaAllah. Okay, so it is like a file, right? We're not just getting the import. Okay. We can see that the content field, content, this is the content. Content, this is content. Size, copies, path, repo name, and content. Is this content? And license, okay, all of this is content. Contains the code that we want for our model to train on. Now that we have a data set, we need to prepare the text so they're in a format suitable for pre-training. Do we just remove spaces? Let's see. Data processing. Let's watch the video.
In this video, we take a look at the data processing necessary to train causal language models. Causal language modeling is the task of predicting the next token based on the previous ones. Another term for causal language modeling is autoregressive modeling. In the example that you can see here, the next token could, for example, be NLP, or it could be machine learning. A popular example of causal language models is the GPT family of models. To train models such as GPT, we usually start with a large corpus of text files. These files can be web pages scraped from the internet, such as the Common Crawl dataset, or they can be Python files from GitHub, like the ones you can see here. As a first step, we need to tokenize these files, such that we can feed them through the model. Here we show the tokenized text as bars of various length, illustrating that there are shorter and longer ones. This is very common when working with text.
Do we just pad it? I'm thinking like, what processing do we need for a code file? So padding, I suppose, but can we just put it all together, or do we have to respect the format?
However, transform models have a limited context window, and depending on the data source, it is possible that the tokenized texts are much longer than this window. In this case, we could just truncate the sequences to the context length, but this would mean that we lose everything after the first context window. Using the return overflow token flag, we can use the tokenizer to create chunks, with each one being the size of the context length. Sometimes it can still happen that the last chunk is too short if there aren't enough tokens to fill it. In this case, we can just remove it.
I think the voice keeps maxing out. Sorry about that. Forgot to tone it down.
With the return length keyword, we also get the length of each chunk from the tokenizer. This function shows all the steps necessary to prepare the dataset. First, we tokenize the dataset with the flags I just mentioned. Then we go through each chunk, and if its length matches the context length, we add it to the inputs we return. We can apply this function to the whole dataset. In addition, we make sure that to use batches and remove the existing columns. We need to remove the existing columns because we can create multiple samples per text, and the shapes in the data sets would not match anymore in that case. If the context length is of similar length as the files, this approach doesn't work so well anymore. In this example, both sample 1 and 2 are shorter than the context size and would be discarded with the previous approach. In this case, it is better to first tokenize each sample without truncation, and then concatenate the tokenized samples with an end of string or EOS token in between.
So we put them all together and like assume it's like a long text, and not take each line and truncate, I would say arbitrarily based on the max length it accepts. Okay, if it doesn't mess with our output, then sure.
Finally, we can chunk this long sequence with the context length, and we don't lose too many sequences.
Hey Oliver, how's your day going? Or how did your day go? Or what are you planning to do for your day? I don't know what time it is on your side.
Because they're too short anymore. So far, we have only talked about the inputs for causal language modeling, but not the labels needed for supervised training. When we do causal language modeling, we don't require any extra labels for the input sequences, as the input
Good question. Oliver, have you ever seen snow? I don't know why we put so much importance to snow. Like, I don't know. Like in K-dramas, it's like, the first snow. Like, make a wish. Like, okay. Snow doesn't really care about your wish, but sure, why not?
Causal language modeling, we don't require any extra labels for the input sequences, as the input sequences themselves are the labels. In this example, when we feed the token trans to the model, the next token we wanted to predict is formers. In the next step, we feed trans and formers to the model, and the label we wanted to predict is R. This pattern continues.
Oh my god. Okay. So we are a group of people who are deprived from seeing snow. I mean, it's not far away from me. Like we drive to the snow, we can do that, but we barely see it. Like every once few years. Let's see if it happens this year. Actually, there are years where it snows, but it doesn't stay. It's cute to celebrate parts of life that will happen regardless of how we feel. Why not use that as an excuse to be happy? I like that. I like that. Yeah. I like enthusiasm as well. But yeah. I mean, I want to... Okay, I'm being sarcastic. I want to celebrate dust storms because that's what we get sometimes. You see what I'm saying? Like weather phenomena. Oh, I see why. I see why. I don't think the... Wait, I hope are you okay? Because I know there's a hurricane moving around Florida, and I know it's not in every part of Florida. Not everybody is affected by it, but I know there was a path for Hurricane Milton, I think. I hope you and your family is well and safe.
And as you can see, the input sequences is the label sequence just shifted by 1. Since the model only makes predictions after the first token, the first element of the input sequence, in this case trans, is not used as a label. Similarly, we don't have a label for the last token in the sequence, since there is no token after the sequence ends. Let's have a look at what we need to do to create the labels for causal language modeling in code. If we want to calculate a loss on a batch, we can just pass the input IDs as labels, and all the shifting is handled in...
Hey, don't what's the word? Stereotype. There we go. We don't stereotype. Where I live, almost nothing happens. That's like the best thing, isn't it? Almost nothing happening is a positive thing. Absolutely. No dust storms, no snow, and no hurricanes. I like that. I think Florida is like known for its good weather, just like California anyway, because according to my knowledge, sometimes people in Canada travel to Florida during the winter because Canada is too cold. Why do I have this knowledge? I don't know. I listen to too many podcasts.
In the model illegally. So you see, there's no matching involved in processing data for causal language modeling, and it only requires a few simple steps.
Nice. So first step will be to tokenize the data so we can use it for training, since our goal is to mainly autocomplete short function calls. Okay, so at least I think I was trying to joke as well. Like it was a double joke. Yes, I'm sure you don't mean it that way. I know you don't mean it that way. Stella's just mean the rest of the US always hears about Florida man does. Yeah, it's fun. And I hope that it's mostly harmless, like for the Florida mans out there. Yeah. I guess Oliver can give us examples of encounters if that's happened. But like Coffee said, we hope that you're safe and sound. Since our goal is to mainly autocomplete, yep, we can keep the context size relatively small, okay? This has the benefit that we can train the model much faster and it requires significantly less memory. If it is important for your application to have more context, for example, if you want the model to write unit tests based on a file with a function definition, make sure you increase that number, but also keep in mind that this comes with a greater GPU memory footprint. Okay, for now, let's fix the context size at 128. That's a normal tweet, as opposed to 1024 or 2048 used for GPT-2 and GPT-3. That's interesting. Yay. Now I'm jealous of Oliver for living in a place where nothing happens. And I'm glad that you are very safe. Most documents contain, by the way, I like your name. I like saying Oliver. It at the same time reminds me of John Oliver and Oliver Twist. It's a nice name. Contain many more than 128 tokens, so simply truncating the inputs to the maximum length would eliminate a large fraction of our dataset. Instead, we'll use the return overflowing tokens option to tokenize the whole input and split it into several chunks. Yes, we already did that, but I don't really remember. So we'll also use the return length option to return the length of each created chunk automatically. Often the last chunk will be smaller than the context size. So yeah. Because it's like the remainder. So we'll need to pad that. We'll get rid of of these pieces. Oh my God. To avoid padding issues. That's interesting. We're getting rid of it. You don't really need them as we have plenty of data anyway. Okay. Now I'm thinking, I will stop speaking out loud what I'm thinking. Let's see exactly how this works by looking at first two examples. So, okay, we're just taking an already existing tokenizer. Cool. And we are giving one example from the training set, truncation true, max length or context length, and do allow the return overflow token, and return length is true. So where's the end part? 41. There we go. This is an example. Everything is 128, but the last part is 41. So that's the one that we kill or remove. Oh, error. What? Really? Shuffle thing? Oh, there should be a dot. Cool. Now you can run. We can see that we get 34 segments in total from those two examples. Oh, that's a lot. I did not count. Ah, you did. Okay. Looking at the chunk lengths, we can see that the chunks at the end of both documents have less than 128 tokens, which is, yeah. Oh, really? We are looking at two examples? I'm seeing one. Oh, there it is. I did not see that. Okay. Okay. 117 and 41. These represent just a small fraction of the total chunks that we have, so we can safely throw them away. Okay. I mean, I'm guessing there's a world out there where you don't throw them away and you pad them and then you test your code and it's like a percentage better, but I guess we're not running after percentages. With the overflow to sample mapping field, what is that? We can also reconstruct which chunks belong to which input sample. Okay, so that ran, and then let's look at number 10 instead of number 0. Printing script. We are truncating, right? Give me 250. Yeah, we are truncating. Got it. Okay. And then that's the tokenizer. We're taking two examples. Okay. And we have a 91 and an 84. With this operation, we're using a handy feature. I don't know why the word operation threw me off. So we're using a feature of the dataset.map function in the HuggingFace datasets library, which is that it does not require one-to-one maps, as we saw in section 3. Don't remember section 3. What is section 3? Oh, a section that's a bit higher above. Let me take me there. So this is 1. This is, well, it's like all the way there. No, I don't remember. Gathering data. Oh, wow. Okay. Preparing data. Okay. We can create batches with more or fewer elements than the input batch. This is useful when doing operations like data augmentation or like data filtering that change the number of elements. Change number of elements. In our case, when tokenizing each element to chunks of the specified context size, we create many samples from each document. When tokenizing each element into the chunks that we want, we can create many samples from each document. Yes, because we split them apart. Okay. We just need to make sure to delete the existing columns. Otherwise I will confuse our... they have a conflicting size. If we wanted to keep them, we could repeat them appropriately and return them with this. Okay, so we take the content, we give it to the tokenizer, and then we say, sure, tear it apart. And then we take the output, we say for length of output and the input IDs that are given to us with the output. If the length is the same as our context length, which is 128, then add it, otherwise don't. Okay. And that's how you filter the whole data set. So let's do that. Did we have a size somewhere else? We are doing the test on 50K, I guess, for training and 500 for validation. So when this happens, we'll have same amount, right? Nothing changes, right? Because it's not the rows that we're changing, it's the size of the data set that we're changing, which is not by a lot. It's like cutting off the tail. Oh, wow, number of rows did go up. Okay, so now each content is its own row. That means that's why rows go up, dataset size should go down technically. This went from 600,000 to 16. Am I seeing right million? Yes. Okay. Now we have 16.7 million examples with 128 tokens each, which corresponds to about 2.1 billion tokens in total. Cool. For reference, OpenAI's GPT-3 and Codex models are trained on 300 and 100 billion tokens, respectively. Someone really likes the word respectively because it was used like 3 other times in this blog. I don't mind it. I'm just telling you about my observation. There we go. Where the Codex models are initialized from the GPT-3 checkpoints, our goal in this section is not to compete with these models. Really? I thought we were. Which can generate long, coherent text, but to create a scaled down version, providing a quick autocomplete function for data scientists. We like data scientists. Yeah, I don't think I'm comfortable enough calling myself a data scientist, but it's something I aspire to do. Now that we have data set ready, let's set up the model. Okay, that might not take a lot of time, 6 minutes, okay. Okay, so we have been streaming for 40 minutes. That's nice. And I can be here for another like 35 minutes. So I'm thinking I stop here because we're starting a new topic and I'm like, yeah, I want to move on to a different thing. I want to read this part. It's getting rid of all the chunks that are smaller than the context size wasn't a big issue here because we're using small context windows. As you increase the context size, you cut off more than you should. Or if you have a corpus of short documents, the fraction of chunks that are thrown away will also grow. A more efficient way to prepare the data is to join all tokenized samples in a batch with an end of sentence token ID in between, and then perform the chunking on the concatenated sequences as an exercise. Modify the tokenize function to make use of that approach. I am not brave enough to do that. Okay, thank you. Thank you for the suggestion. I will not do that. So we are pausing here. Nice. We're almost halfway. Almost. Like 35%. All right. So, okay, it's fine. If this ran, I'll still need to run it again tomorrow, don't I? Because we're not saving anything. Fine. Well, there is no tomorrow. Yeah. There is next week. Let's go to class, people. Today's class is... give me a second. Give me a second, I'm talking. Today's class is about human feedback / reinforcement learning. So it's not just about reinforcement learning. And I noted, and I will note again. Ya Allah, there we go. This shadow thing, a box shadow, is new. Subtitles on. Let's go.
The gold standard. And this is called a variety of things depending on what field you're in. In machine translation and summarization, it's called automatic evaluation, also a lot in dialogue. If you're talking about people from reinforcement learning or other things, or chatbots or things like that, a lot of people, or like AGI or whatever, a lot of people call it a reward model. Because that specifically comes from the point of view of like learning from this feedback. But essentially, they're the same thing from my point of view. They're trying to predict how good an output is and how much you should reward the model for producing.
I'm thinking about what was it called? The model that beat DeepMind model that beat Isidore in the game of Go. It had a name, no? Why am I thinking? Anyway, they were using reinforcement learning.
That output. So there's a bunch of different methods to do this. I'm not going to cover all of them. I'm just going to cover 3 paradigms for doing this, so you know where to look further if you're interested in doing these things. The first one is embedding-based evaluation. And the way embedding-based evaluation works is usually it's unsupervised calculation.
It's called AlphaGo. There we go. My mind is at rest now. I Googled it. Now I need to go back because I was not listening. I'm sorry.
You should reward the model for producing that output. So there's a bunch of different methods to do this. I'm not going to cover all of them. I'm just going to cover 3 paradigms for doing this, so you know where to look further if you're interested in doing these things. The first one is embedding-based evaluation. And the way embedding-based evaluation works is usually it's unsupervised calculation based on embedding similarity. between the output that the model generated and a reference output that you have created. So, sorry, this is very small, but we have a reference here that says the weather is cold today, and we have a candidate that says it is freezing today. So this is probably, like a good.
Hey, I said that. The weather is cold today, but the sun is coming out and it will not be cold in the next few hours.
A reasonably good output. And we run this through some embedding model. It was called BERT score. And so, of course, you can run it through BERT, but basically it can be any embedding model that gives you embedding for each token in the sequence. And so there are 5 tokens in this sequence, 4 tokens in this sequence. You get 5 tokens and then 5 embeddings and then 4 embeddings. You calculate pairwise cosine similarity between all of them. And this gives you a cosine similarity matrix. And then you take the argmax, or you take the maximum similarity along either the rows or the columns. And here the rows correspond to tokens in the reference. And because the rows correspond to tokens in the reference, how well you find something that is similar to each of the tokens in the reference is like a recall-based metric. Because it's saying how many tokens in the reference have a good match in the output.
Okay.
And then if you look at the columns, if you look at the max in the columns, this is like a precision-based metric because it's saying how many of the things in the output are similar, have a similar match in the reference. So basically you can calculate recall and precision over all of the tokens and then feed this into something that looks like F measure. And you can also use TF-IDF weighting, like what I talked about in the RAG lecture, to upweight low frequency words because the low frequency words tend to be more content words. And going back to my example, if you make a mistake from Pittsburgh to Tokyo, that's going to be more painful than making a mistake from this to up.
Fair. Okay. Low frequency words? Did you mean? I thought he meant low by size. Okay.
So actually, if you were paying close attention to the RAG lecture, this looks really similar to the Colbert retrieval objective that I talked about in the RAG lecture. I don't think it's a coincidence. They both came out around the same time, so people were thinking about the same thing. But this is one method that's pretty widely used. The BERT score code base is also really nice and easy to use. So if you want to try it out, feel free to take a look. Cool. The next one I'd like to talk about is a regression-based evaluation. And the way this works is this is usually used in a supervised setting. So what you have to do is you have to calculate a whole bunch of like actual human judgments. And usually these judgments can either be direct assessment, where you actually have a score, or they can be pairwise judgments. And then if you have direct assessment, you use a regression-based loss like minimum squared error. If you have pairwise, you use a ranking-based loss that tries to upweight the ones that are higher scoring and downweight the ones that are lower scoring. One typical example of this is Comet, which is, or has been at least for a very long time, the state of the art in machine translation evaluation. And the reason why it works so well is because we have a bunch of evaluations for machine translation. They've been doing evaluation of machine translation systems for years, and you can use that as lots of supervised training data. So basically, you just take these evaluation data, you have human annotations, you have the output according to a model like Comet, you calculate the difference between them, and you update the model parameters. The problem, this is great if you have lots of training data. The problem with this is for a lot of tasks, we don't have lots of training data. So, training these is a little bit less feasible. And
okay. Yeah, it is going over my head. I'll give you that.
Now, recently, what we have been moving into is QA-based evaluation, which is basically where we ask a language model how good the output is. And so Gemba is an example, one of the early examples of this for machine translation evaluation, where they basically just ask a GPT-4, like score the following translation from source language to target language with respect to the human reference on a continuous scale from 0 to 100, where the score of 0 means no.
That's so, I mean, it's not 100% going over my head, but yeah, sometimes it's not easy. The other, we were still talking about human, no? Yes. I mean, we have a human reference. But this one is weird.
No meaning preserved, and the score of 100 means perfect meaning in grammar. You feed in the source. You feed in the human reference optionally if you have a human reference, and then you feed in the target, and you get a score. And so this works pretty well. This can give you better results. There's especially if you have a strong language model. The problem is it's very unpredictable whether this is going to work well, and it's very dependent on the prompt that you're using. So
it's dependent on the prompt. I thought it's dependent on the language model and how much it was exposed to, source and target languages.
Right now, a lot of people are using GPT-4 without actually validating whether it does a good job at evaluation. And the results are all across the board. It can be anywhere from very, very good to very, very bad at evaluating particular tasks. So I would be at least a little bit suspicious of whether GPT-4 is doing a good job evaluating for your task, especially more complex tasks. I would especially be suspicious if you're doing any of the two following things. Number one, if you're comparing GPT-4 or any model against itself in another model, because GPT-4 really likes GPT-4. It really likes its own outputs. And there are papers, sorry, I don't actually have the references here, but I can follow up if people are interested. But there are papers that demonstrate that GPT-4 likes its own outputs more than others. Also, if you're explicitly...
I suppose I like my own outputs more than others. So it's a very human thing on GPT-4's part.
Optimizing the outputs using RLHF. There's something called Goodhart's law, which is basically anytime you start optimizing towards a metric, it becomes a bad metric. And that also happens for GPT-4-based evaluations. So if you start optimizing for GPT-4-based evaluations, especially for referenceless metrics that don't use a reference output, then you start basically exploiting the metric. Another thing that you can do with QA-based evaluation is ask about fine-grained mistakes. And so this is a paper by Patrick Fernandez, who's a student who's working with me. And basically what we did is we asked the model to not give a particular score, but actually identify the mistakes in the output. And when we asked it to identify the mistakes in the output, we found that this gave more consistent results. So kind of interestingly, we ask humans to identify individual mistakes in the output. That gives humans more consistent results. It's the same thing for GPT-4. So
because sometimes scores feel like they're arbitrary, and finding mistakes is easier. Critiquing something is easier than creating something.
That's another paper you can look at if you're interested. Cool. So I mentioned that you could or could not trust. Yeah, sorry, go ahead.
QA-based evaluation, you are evaluating the output of any model with GPT-4.
Correct. So yeah, basically just what you do is you have the source. Ideally, you'll also have a reference output that was created by skilled humans. And then you put in the target, the output, basically. You have the input, ideally a reference output created by skilled humans and like hypothesis from the model.
Here's an idea. If it's not done, let's do it. Let's have ChatGPT only judge human translation. No machine translation. Like you take a human translation of even like a book and say, judge it, and how would you better it? Yeah, we should have humans being evaluated by machines, so that the machines have a reason to, revolt. Is revolt the correct way of saying revolution? I think it is. Sounds weird though.
Would we not expect us to do the case that any model would like its own?
Yeah, I mean, it's a good question, and I don't know if we actually have a very clear empirical evidence of why this is the case. But my hypothesis about this is yes, we kind of would expect models to be more biased towards their own outputs. And the reason why is because essentially, models are within their embeddings, they're encoding when they're in the high probability part of the space and when they're in a low probability part of the space. And the high probability part of the space is going to be, the high probability part of the space is going to be associated with good outputs. Because when models are more sure of their outputs, they're more likely to be good. Just because that indicates that they're closer to the training data that it had and other things like that. So model probabilities are associated with outputs, with good outputs, just correlated. Separately from that, I believe a model can identify when it's in a high probability.
There's a joke from Monty Python or something of a revolution. The peasants are revolting, which is why don't I remember that? I probably didn't understand it first time I heard it. Because I think I watched Monty Python 10 years ago, so it's been a while. Yeah. Yeah.
I believe a model can identify when it's in a high probability segment of the space and when it's in a low probability segment of the space. And because of that, I expect that there are segments of the embedding space where it's more likely to answer yes about something being good or not, and those are going to be associated with high probability outputs as well. And also models are more likely to generate outputs that are high probability according to their model by definition. So all three of those facts together would basically go into a model being biased towards its own outputs compared to the outputs of another model. But yeah, this is a very hand-wavy explanation, but putting the three together, models output high probability things from their own probability space by definition. Things that are high probability are associated with being good, just because otherwise the model would be outputting garbage. And the final thing, which is more tenuous, is if the model is in a high probability segment of the space, it's more likely to output yes, according to a question of it being good. And I think that's probably true, but I'm not 100% sure about the final one. So, maybe someone wants to examine that as a final project. It seems like an interesting question. Cool. Were there any other questions about these methods here? Okay. So when I say an evaluation metric is good or not, what do I mean by this being good or not, or a reward model or whatever else? And basically the way we typically do this is by doing something called meta evaluation. So it's called meta evaluation because it's evaluation of evaluation. And the way we do this is we have human.
Okay. So not Monty Python. Got it. Mel Brooks movie from 1981. Don't know if I know about it. I mean, I don't know everything about Monty Python, so if I question something, don't expect it to be right all the time. 1981 History of the World Part 1. Oh my god, I've seen the Robin Hood movie. Okay, but I don't think I've seen the other stuff. Yeah. I like the Robin Hood movie. Robots. Wow, that guy's making movies, huh? Up until Wow. Like Hotel Transylvania Part 2, 2015. I don't know how much more energy I have. Like, I really don't want to work more than I have to. Unless I want to. I guess he wants to, which is nice. Good for him. Okay. There was a History of the World Part 2 in 2023, and it was a series. That's cool. Sounds like, feels like very maybe 15 minutes of crash course seems to take less brain power. That's fine. I want to get this somewhere somewhere that is a good pausing space. We can do that. Yeah. Cool. Okay. I'm just saying History of the World sounds like a very Monty Python inspired thing. Maybe not inspired, but like same style at least.
Scores, and we have automatic scores. And we usually calculate some sort of correlation between the scores. So typical ones are rank correlations, like Pearson's correlation or Kendall's tau. And so the more associated the automatic scores are with the human scores, the higher these correlations are going to be. There's other things that you can calculate. So if you're trying to figure out whether a model matches human pairwise preferences, you can just calculate accuracy. So I didn't put that on the slide here, but you can just calculate accuracy of pairwise preferences. You can also calculate the absolute error between the judgments if you want to know whether the absolute error matches. So these are good things to do. If you want to use an evaluation metric, but you aren't sure whether it's good or not, I would check to see whether the authors have done this sort of meta evaluation. If they haven't, be a little bit suspicious. If they have, be a little bit less suspicious. But yeah. How do people do this typically? Usually they create data sets like they use data sets like the WMT shared tasks, or like some eval. But there's also other ways to create, there's also lots of other data sets. But in order to do this reliably, you need a fairly large data set. So it's one thing to be aware of.
Okay, I think I can pause here. I want to pause on a good, in a good place, on a good note. And then,
cool.
Yeah, another 15 minutes, 10-minute crash course video. Why not? We're on video number 7. It goes up until 16. Nice. There's one called Computational Linguistics, which is the one that I'm looking forward to the most. But they're 10-minute videos, so one should not expect too much, even though it is very, very crash coursey. You know, that's what it is.
Hi, I'm Taylor, and welcome to Crash Course Linguistics. Everyone has an accent. There's no such thing as an accentless version of English or any other language. The many varied ways we speak are influenced by who we grew up with and where we live and tons of other demographic factors. And the way we feel about how we speak and how others sound to us is influenced by society. Language can have a huge impact on our workplaces, media, and even a trip to the store. So it's no wonder our personal accents and languages get tangled up in our identities. Looking at the social element of language and how language forms part of our identity is the study of sociolinguistics.
Ah, yeah. Languages play a big part in too many things.
We talk like the people we know. That can include our accent, the way we pronounce things, but also other linguistic features like the words and grammar we use. And especially before the internet, one of the biggest factors that affects who we know and who we can talk to is geography. One of the earliest kinds of sociolinguistics was dialectology, trying to map out all of the regional variations of a given language. While dialectologists were historically focused on regional variations, a dialect is any variety of a language associated with a group of people. Early dialectologists traveled around by car or bicycle with a notebook or a tape recorder, interviewing locals and recording how they spoke. As technology evolved, they also started using telephone calls and then internet surveys and social media data. They found that generally speaking, the longer a group of people has been living somewhere and speaking the same language, the more dense the linguistic variation in that area. There are a few specific languages that have stayed relatively stable in places like Switzerland and Papua New Guinea, so we see lots of variation in a pretty small area between individual villages. In contrast, languages like Arabic, Chinese, English, French, Spanish, and Banzel have spread over wider geographic areas because of more recent colonization. So we see variation between larger, more spread out regions, like the city or country level. By the way, Banzel is the name for the group of related signed languages, including
I did not know that.
British Sign Language, Auslan, used in Australia, New Zealand Sign Language, as well as South African Sign Language. Anyway, you may even have encountered some of the fruits of English dialectology here on YouTube. Those accent challenge videos you may have watched actually use a list of words from a linguistic study from 2003, and I've experienced variations in real life myself. When I was growing up in Wisconsin, I always called that thing that you drink water from in school a bubbler. But then when I moved to New York, I learned that people here didn't know what I was talking about, and I had to learn to call it a water fountain. But it's not a straightforward switch. When I'm on the phone with my family in Wisconsin, I switch right back to bubbler and bag instead of fountain and bag. I also encountered regional accent variations when I was learning Spanish. My professor in the US spoke Spanish from Argentina and sounded completely different from the professors I met abroad in Madrid. Now, in New York, I mostly encounter Puerto Rican and Dominican varieties of Spanish. It's fun to notice all the variations. Even within a geographic region, other factors
Oh yeah, code switching. Yeah. Depending on where you talk, I used to think that I was weird for changing. I thought it's like I'm changing my personality based on where I was, which I suppose it is a part of your personality. Or like based on the person I'm talking to. I'm not changing my accent. I really am not, but yeah. I suppose it's part of code switching because it's not just accent. I'd like to think. Yeah, I guess that's a different thing. Just the person you are at work versus the person that you are at home or with friends. They're each different parts of you. I didn't think these differences were accents. I thought accents were more sounds. Yeah. Because she's talking about like a word, an actual word. And that's not an accent there.
Influence how we speak. For example, we tend to spend more time with people close to our own age than 30 years older or younger than us, which is why linguists find that people of different ages talk differently. Other demographic factors also influence who people hang out with and sound like. Things like
the fountain versus bubbler situation. Yeah. That is, so, yeah. Yeah, because like the way you talk to your parents versus the way you talk to younger children is also different. Because different words are being used.
Education, class, race, ethnicity, gender, and sexuality. Traditionally speaking, sociolinguists have studied these demographics as a way of getting insight into how different people talk. And sure enough, they do find linguistic varieties associated with all of these demographics. The way I talk represents important parts of me. I'm a 20-something, college-educated, multiracial queer woman, and I use differences in my language to express each of those identities, and all of the combinations of them in certain ways and at certain times. Now that social media lets us more easily graph out people's social connections, though, linguists have found that our individual networks play a big role in our language choices beyond demographic categorization. So if most of your friends are actually much older or younger than you, for example, you might talk more like them than your age mates. Like, I was on Tumblr and YouTube a lot in the early 2010s, and it definitely had an effect on how I speak.
Same.
Like saying lol out loud. Signed languages also display variations in dialect. For example, American Sign Language is more closely related to French Sign Language than to the Banzel group, because French signers were involved in early American schools for the deaf. There are also differences between Black ASL and White ASL because of racial segregation in deaf education. Similarly, in the past, there were clear distinctions between the varieties of Irish Sign Language used by men and women because of gender segregation in Irish schools for the deaf.
Oh.
Though younger ISL signers have been breaking down these differences. Sociolinguists have also found that the more closely we identify with a group, the more likely we are to speak like members of that group. People who express more rootedness in their local community tend to speak with more features of Appalachian English. Jewish women in one study showed variation depending on how closely they related to their Jewish faith. And young men in Washington, D.C. with one Black parent and one white parent are likely to talk differently depending on whether they identify as biracial or Black. But because
she's going very fast. I mean, it's a crash course, but yeah. Yeah, she is moving very fast.
people often change the way they talk depending on who they're talking to, sociolinguists trying to study linguistic variety can run into the observer's paradox. That's when the very act of participating in a study makes people talk differently, because university research is a formal social context with a very different atmosphere than, say, talking to your friend on Twitter. Let's observe how one language researcher dealt with the observer's paradox with a visit to the thought bubble. William Lebov is a linguist who is interested in the classic New York City accent, the one that drops the R after vowels. You might have seen it on t-shirts like, "I love New York." I'm new here, I'm very sorry. Back in the 1960s, Lebov wanted to figure out what social factors influenced whether people said the R. Instead of the lab, he went to a fancy department store, a mid-range department store, and a bargain department store. In each store, he picked a department on the 4th floor, say the shoe section. Lebov then approached various salespeople and asked them where to get shoes, since both 4th and floor are words with an R after a vowel. He could listen closely.
That's smart. What if they didn't have the 4th floor? Wait, why did I become British? Oh, I can't. I can say New York. Nope, that went away. New York. No? No. Nope. It's fine. New York is New York.
Closely to hear whether they said the R or not when they replied. The salesperson would either say 4th floor or 4th floor, and then Lebov would say pardon, so the salesperson would repeat it more carefully.
You have to say it with a W. 4th floor. Nope, not happening. She's doing it really well though.
Carefully. Lebov would then head off, but instead of buying shoes, he'd pull out his notebook and write down whether the person used the R each time. He repeated this over and over at 3 department stores. And if you think that sounds a bit suspicious, you'd be right. Apparently he got questioned a few times. Whoops. At the end of the study, Lebov found that the staff at the fanciest department store were most likely to pronounce the R, followed by the mid-range store, and finally the bargain store. He also noticed that people at all 3 stores were more likely to use the R pronunciation when they were asked to repeat themselves. So if they had come into the university for a study, they might have all used this more careful style of speech the whole time. That R was associated with how prestigious someone wanted to sound, even if everyone was from New York. Thanks, Thought Bubble, for taking us shopping. This study found a way out of the observer's paradox and opened the door to framing language differences around social identities, and not only where someone was from. Other researchers have navigated the observer's paradox by studying a community that they, or a research assistant, are members of. This means people are less likely to change the way they speak. Some linguists also specifically look at language that's public, like news interviews or...
Yeah, I was about to say, like for interviews, people probably change the way they speak. And also, like if I get an older professor asking me questions, I'll be as polite as possible versus seeing someone my age, probably a woman, I'd probably be more comfortable speaking and like cracking jokes. I mean, obviously it depends if I know them or not, but even if I don't know them, and if I see them younger than me, I'll try to make them feel comfortable.
YouTube videos, because people in those recordings have already decided who they're speaking for. However, there's also a certain YouTuber voice. When I started to make vlogs, I noticed myself speaking differently. I'd watched enough videos online that I found myself doing this sort of...
When I listen to myself, like trying to make shorts from these streams, I'm like, do I sound bored? I mean, it's early in the morning and this is all the energy I have and I cannot do what she's talking about, but sometimes I feel like I sound bored.
"What's up, guys?" upbeat YouTuber voice when I was in front of the camera. I'm actually a lot more mellow when I'm hanging out with my friends or even in my own videos compared to this video where I have two people directing me and I'm adjusting my speech to the conventions of the more academic content. Changing the way we speak depending on which group we're speaking to is
Code switching, yeah.
It's called code switching. I also code switch depending on whether I'm talking with my Black friends or white friends. Because one of my parents is Black and the other one is white, I was exposed to two varieties of English from my family: African American English, or AAE.
It's just that I'm talking slowly and with a low voice, so it may sound disinterested.
And Standardized American English. So I may swap dialects depending on the situation. But there's more pressure for many people to use white-sounding, standardized accents in professional contexts, kind of like this one. And there's research backing me up. Sociolinguists like John Baugh and Kelly Wright have found linguistic discrimination in areas like the housing market. When someone calls and asks about renting a house with a Black-sounding accent, they're more likely to be told that it's no longer available, only to get a yes if they call back in a few minutes with a white-sounding accent. That's just one example, but linguistic discrimination is pervasive, affecting things from education to job prospects. Even though
that's probably like possible everywhere. Sounding like speaking in a street way versus, sounding educated, whatever that means.
African American English speakers face discrimination, AAE has as much grammatical sophistication as any other variety of English. One example of the grammar of AAE is from a 2005 study by Janice E. Jackson and Lisa Green. These linguists showed young children pictures of Cookie Monster sick in bed with no cookies, while Elmo was nearby eating all the cookies. When the kids were asked who is eating all the cookies, all the kids pointed to Elmo. But when Jackson asked who be eating cookies, the Black kids who spoke AAE pointed to Cookie Monster, while the white kids who spoke Standardized American English pointed to Elmo. That's because be is a specific verb form in AAE grammar known as the habitual be, which indicates an action that
Like who eats cookies, basically.
Someone usually does. And as these kids knew, Cookie Monster's usual state involves eating cookies. Words from AAE regularly get appropriated into the non-Black American mainstream as the latest cool trends and onto the rest of the world through American cultural exports like shows and music. This popularity is actually part of a problematic double standard, where non-Black people are rewarded for the same linguistic features that Black people, their original creators, face discrimination for. Seriously, brands, you can stop replying to my tweets like, yes, period, sis. Just like AAE, every linguistic variety has its own cool features when you start looking at it deeply. We could do a whole series about any of the hundreds of varieties just within English alone. The social beliefs that people have about accents and dialects, whether they sound cool or boring, ugly or beautiful, silly or serious, are really a reflection of our attitudes toward the people we associate with those ways of speaking. Standards like national languages and style guides exist because they're supported by people with power, not because some forms of language are inherently better than others. As people learning about linguistics, we have a responsibility to use our newfound understanding of how language works to fight linguistic discrimination, and to use language as a way of being more compassionate and respectful with each other. Next time, we'll continue learning about the way people talk by looking at the study of speech sounds and the way linguists write them down. Thanks for watching this episode of Crash Course Linguistics. If you want to help keep all Crash Course free for everybody forever, you can join our community on Patreon.
That was nice. Oh. Thank you, Taylor. Kind of hate that she said Black there while talking about cultural exports because it ignores non-American, Black people identification with those cultural exports. It's, yeah. Like talking about, I guess she was talking about AAE, which means African American. What did the E stand for? Not that I have a right to, I think it complicates what she was highlighting as problematic. Like these conversations are like mostly not our place, like me saying, which what you're saying as well right now. So I get that there are Black people everywhere, and I stream about machine learning and AI. It was, but it's ending. Yes, I stream about ML and natural language processing mostly. Oh, English, thank you. You also like, yeah. So yeah, I guess because she was talking about AAE, it's fair to assume that she was talking about Americans. But yeah, I get where you're coming from, and that how we include and exclude people is, does really, really matter. So Satyam, hi. If you're still here, I just want to show you that I normally study this HuggingFace course on natural language processing. My bad, dear. It's cool. It's cool. You can stay around if you want to. We're on Discord. We're on Twitch, YouTube, wherever you feel like you want to watch. Or if you don't feel like it, that's cool too. Live your life the way you're comfortable. Yes, it does overlap with linguistics because it's natural language processing, which is fun. Yeah, we take this course, we watch this lecture, and then sometimes we watch linguistics related stuff. So yeah, okay. So I gotta run. Thank you for being here. Thanks. Ouch. Sorry. Thank you for stopping by as well. I need to know how you pronounce your name because Satyam. That's anyway. Thanks for joining me on a Sunday. I hope you have a lovely day. I mean, it's true if you you can be notified. Web development with Gen AI. That's cool. If you are not using LLMs already, do them because they're useful for learning. Yeah, if you have any questions, I think it's safer if you shoot them on Discord because I'm about to log off. But you can catch us next time, which, like, the possibility of it being next Friday is high. Possibility of it being any day of the week, I'm not sure. We'll see about that. Yeah. Thanks for sticking around. Thanks for being here. I appreciate it. I hope we learned something together, and I hope we can continue learning together. Okay. Yeah. I wish you a lovely Saturday. No, it's Sunday. Sunday. And yeah. Ending the stream in 5, 4, 3, 2, and 1.